Okay, so in this second video, we're going to talk about something called the electric potential, which has the symbol capital V, and we'll talk about like how it's different from the electric potential energy, which, as we talked about in the last video, has the symbol capital U and has like very similar parallels to potential energy in a gravitational sense. Okay. So the definition of electric potential, V. So V is the symbol for electric potential. And the definition is basically just the amount of potential energy per unit charge. So it's the amount of U, right? Remember, which is electric potential energy in this context per unit charge. Okay, at a specific point in space. Okay, so at a specific point, and to be more specific, we should say in an electric field. Okay, so like we might have an electric field that is created by this like positive Q, right? And we might want to know like what is the potential at this point here. Okay. And so we're always talking about like potential like within an electric field. Okay. So the symbol for it is V, and to do so it's very easy to calculate. You're just basically taking the potential energy and dividing it by Q. Okay, so it's U divided by Q. The unit for it is the volt. Okay, and so so because U is in units of joules, right? And this is charge, which is in units of coulombs. The volt is defined as a joule per coulomb. Okay, or like J over capital C. Okay, so this is the way I think about this. So just as the electric field removes like the test charge from the force equation, that so too does the potential remove the test charge from the electric energy formula. So the two things are similar, like they can be thought of in the same terms. So like remember when we went from Coulomb's law, right? Remember that's Coulomb's law. When we went from there to electric field, um, the only difference between Coulomb's law and electric field is that the electric field is independent of like the test charge. Like you can have a field just in space and it's there as a function of stationary charges that are placed in space. And it's not dependent on like a test charge that you put in that field. It's like it's there just as a function of the configuration of charges that are creating it. Okay. Whereas if you want to talk about an electric force, you need to like you need to put another charge, like a test charge, a Q2 in that field, right? So like the way I think of this, like, is that this part of the equation of Coulomb's law is like creating the electric field. And then that electric field is exerting a force on like some other charge that I put in that field. Okay, it's exactly the same analogy between electric energy and electric potential. Okay, so like electric energy is, remember in the last video, we just said it's like Q1 times Q2 divided by the separation between those two charges, right? R1, 2. Well, to go from electric energy to electric potential, I also get rid of that second charge. Okay, like it's just this. So like the electric potential doesn't need the second charge. Like potential is there regardless of whether you're placing a charge there, if that makes sense. Like you don't have to place a charge there to calculate the potential at a specific spot. Okay, it's independent of the test charge. Okay. So just as so we can say like the change in potential is equal to the change in potential energy divided by the charge, right? I'm getting rid of the test charge. I'm dividing it out, and that equals the negative of the work divided by Q. Okay, so that's just another way of expressing it. Okay. So it's confusing in everyday language because like you'll often run across a case where it's like you've got a 12-volt battery. And you think of like I think it's very easy in everyday language to conflate potential with potential energy because they have like almost the same name, but they're very different. Okay, so let's look at this example of like a car battery versus a motorcycle battery. You could have a 12-volt car battery, and you could also have a 12-volt motorcycle battery. But the car battery has a lot more energy because it has the ability to move a lot more charge. Okay, so like I think this illustrates it quite well. So like remember the electric potential is just the electric energy divided by the charge, right? So if I rearrange that, I can say that the potential energy of that battery is just equal to its potential times Q, right? That's the same exact equation. So let's look at the two examples. The potential energy of a car battery is 12 volts times the car battery can move like 60,000 charges, right? Which is a lot of charges. So 60,000 charges, C, right? And so that is going to have an energy of like 7 times 10 to the power of 5 joules compared to the potential energy of the motorcycle battery, which again is 12 volts. It's a 12-volt battery, but that battery can only move, say, 5,000 charges, right? And so the potential energy of that battery is like a whole order of magnitude less. Okay, so like just keep in mind that voltage is not talking about like how strong a battery is. Like how strong a battery is actually energy. Okay, but obviously the two things are connected. Okay. So now let's look at the relationship between field, which was like last week, right? Electric field and potential. And then the last video of this sequence is going to be looking at that sort of like um, from a diagram point of view. So I'll look at we'll look at some diagrams of like electric field lines and like something called equipotential lines. And like see the relationship between the two things. I think the last video will help kind of like draw it all together conceptually. But the mathematical relationship between the electric field and the electric potential is the potential difference, like the potential is often referred to as potential difference, is just the integral of the electric field over a path within that field. Okay, so what that looks like mathematically is the electric potential is equal to the negative of the integral of the electric field along some path L between point A and point B. Okay, so if I put in, remember, like up here, we said the electric field is just this. So if I let me just kind of drive this for you. If I put in the formula for electric field, so that's Q times K divided by R squared, and I integrate over some path, let me call it R in this context, then the potential difference between those 2 points in the field, so like the potential between those 2 points is just going to be K times Q1 divided by R. Okay, so like again, remember like the integral of like 1 over R squared is just like dr is just 1 over R. Okay, so this is sort of like, and I mean, I get back out like the definition of R, of V, which I defined up here. Okay, so like if I take the integral of the electric field over some specific path, that is the difference in potential between those 2 points. Now, the special thing, and you're going to be encountering this in this week's tutorial, is that because electric fields are conservative, these, the path, it doesn't matter the path that you take between point A and point B. And this week's tutorial is sort of like exploring this exact point. So like the path between A and B doesn't matter. It's what we call path independent. In other words, like let's say I have 2 points, like potential point A and point B. Okay, and they're in some field. Let's say it's a constant electric field pointing to the right here. Okay, and I have some charge and I move it like from point A to point B. And I move it like in one situation, I just move it straight in a straight line between the 2 points. And in another situation, I move it like all the way like around like it goes, I don't know, like a crazy path, like like all the way around, and then it ends up at point B. It doesn't matter. The potential difference between those 2 points is still the same. Okay, so it's like independent of the path. Okay, let me just erase that squiggly line so it doesn't get so messy. But that this is an important point. So like it's only the difference between the 2 points that matter, that the path that a charge takes in between those 2 points doesn't matter. Okay. Another point that's worth mentioning is so because of this relationship and we're always like defining a potential relative to some other point in space. We often say that the point that we're comparing it to is at infinity, where the potential is 0. Okay, so like often to simplify a problem, we ask like, what is the potential? What is the electric potential at this point here? And that question doesn't make sense unless you have some other reference point. But to make the problem easier to think about, our implicit reference point is compared to some distant point at infinity, where the potential at infinity is always equal to 0. Okay, so like, in this integral here, like this would be 0, right? Because we're comparing it to some far off distant point in space where there is no potential. Okay. And then a rule of thumb that we'll get to in the third video is the electric field lines always point towards the area of lower potential. Okay, so like if we look at a parallel plate capacitor, which is an interesting case that we'll deal with in depth next week. Next week is all about capacitors, but this is kind of like a preview. So the positive charge, this side of the plate would be referred to as high potential because it's positive, and this side of the plate would be referred to as low potential because it's negative, right? And the electric field lines, which are drawn in red here in this diagram, are always pointing toward, like, from high potential towards the lower potential. Okay, so when you have a uniform electric field, like in the case of a parallel plate capacitor, this integral, this like V equals the negative. This condenses down, or sorry, simplifies down because of the symmetry of the field to just the electric field times the distance between the plates, right? So I can go from here to here, like where, like let's say that I wanted to take a charge, this positive charge from plate A to plate B. Well, the potential difference between plate A and plate B would just be whatever the uniform electric field is times the distance between those two plates. So if like this was D. Okay, and that's a special case. That's a very nice thing that we'll explore next week when we look at capacitors. That's a very nice thing because it allows us to simplify this this like path integral to just this like very neat formula here. Okay, so and this is like when the E field is uniform. Okay. Okay, so let's look at a couple of examples. So let's say that we have a Van de Graaff generator and it has a sphere like the top of the bulb. So some of you are building Van de Graaff generators for the project, which is very cool. So Van de Graaff generator just looks like this. It's the thing that you see in the science museums where it's like a big metal sphere and there's charge collecting on the sphere. Right, there's like some sort of electrostatic charge separation happening, like there's a belt that's rotating around and charge is accumulating on the outside of the metal sphere. And we're told that the sphere has a radius of 12.5 centimeters. And we're charging, we're putting like so much charge on that sphere that the potential is 100 kilovolts. Okay. And remember, that is only really relevant compared to like a reference point. And so we're saying that the reference point that we're comparing it to is like some infinitely far off distance where the potential is 0. Okay. And we want to know what is the charge, like how much charge is accumulated on the plate, like how many coulombs of charge have accumulated on that that sphere. Okay, so the potential on the surface, and this is important, the potential on the surface is the same as if that charge was located at the center of the sphere. Okay, this is an important point. So like we can kind of pretend that all of that charge is concentrated at the center of the sphere. The reason for that, you've already discovered, hopefully on your own, the reason for that has to do with Gauss's law. If I draw a Gaussian surface around the outside of my sphere, remember this is what we did last week. If I draw a Gaussian surface, right, at some distance r, I can like pretend that all of the charge is concentrated at the center, right? Like as far as Gauss's law is concerned, it's as if all of the charge is concentrated at the center. So I can like, and you can think of it as like if you go very, very, very far away, if you draw your Gaussian surface very, very far away, it's like you just have like this sphere just looks like a point charge, right? It with charge Q, a point charge of charge Q. Okay, so I can calculate. So I know that the potential is going to be equal to K times Q. Q is what I'm looking for, divided by R. And because of this point that I just made, I can just pretend that it's concentrated in the middle, and so I can just really solve for Q. So it's just R times V divided by K. So this is going to be R is 0.125 meters times 100 kilovolts, and then just divided by the constant K. So that's like times 10 to the 9. Okay, and that's just equal to this minus 6 coulombs. So you'd have this much charge accumulated on the outside of that sphere. Okay. So one more example, or actually, no, before we get to the other example, let's just talk briefly about superposition as it applies to electric potential. So just like with field and just like with force, so too does superposition apply to electric potential. Okay, so let's say you had an array of charges like Q1, Q2, Q3, and I wanted to know like what is the potential at this point here at point P. Okay, due to this collection of three charges. Okay, what I would do is just calculate the distance, or not calculate, I would measure the distance. So this would be like R1, this would be R2, this would be R3. And to find the potential, I would just add them up. And the magical thing about electric potential is that it's a scalar, not a vector. So you don't have to worry, you don't have to futz around with direction, which is really nice. Okay, so like it would just be K times the first charge divided by R1 plus K times second charge divided by R2 plus, and so on and so on. Okay, so like it's often easier to get the potential and then to back out of it the field. Okay, that's another strategy for finding field in addition to the one that we did last week, which is Gauss's law, is like if you think of this relationship back up here that we did here, right? If you have the potential, which you can get using superposition by just adding up, like not vectorially because it's a scalar, then you can differentiate to get the electric field, right? It would basically be the opposite of this operation here, right? Where we're integrating the potential to get the electric field. I could differentiate the electric field to get the potential. Okay. So that generalizes to just like the sum of all of the potentials, right? So like if I had some collection of n charges, I could just sum them up over however many charges I had. Okay, so this is basically superposition for how to calculate the electric potential at a certain point. Okay, so let's talk about this example with the electric dipole. So let's say I have a dipole with Q3. So I've got a positive Q, and that's 3 nanocoulombs. And it's some distance, like let's say this is the x axis. And it's some distance like 1 centimeter above the x-axis. And then I've got, remember, a dipole is just where you've got a positive and a negative charge that are equal and opposite, obviously. And they are separated by some distance. So I've got below the x-axis, so like negative 1 centimeter, I've got my negative charge, and that is equal to negative 3 nanocoulombs. And then I want to find the potential at a point located on the x-axis. So there's the x-axis at x equals 3 centimeters. So let's say like this distance here is 3 centimeters. Okay, so I want to know what the potential is here. Okay, so this is like pretty straightforward. And there's symmetry that I can manipulate here. So like this is going to be, let's call this maybe R positive, and let's call this R negative, right? And they're the same because they're the same distances because of symmetry. So the potential is just going to be K times positive Q divided by that distance between the 2 points. And then I'm going to add to that K times negative Q, again, divided by that same distance. And so because of the symmetry, the potential at that point would be 0. It would cancel out. Okay, so okay, oh yes, I have this one other example that I would like to do, but I will maybe do that right at the end of the next video. Okay.